In this module, I am going to talk about a simulation method to calculate the power of a study. Sometimes, for very complicated study design, it's really hard to get a formula for the power calculation or sample size calculations. In that case, the simulation through, power calculation through simulation is a very good method to get the idea about the power or idea about the required sample size. So initially I'll give some concept about these particular methods and after getting a complete concept of this method, then we'll consider a study. I'll briefly describe about the study that will help you to understand the complication that is that might be is the obstacle for finding an appropriate formula for calculating power, and then take one case study, and based on the case study I'll implement in R and show you how the power can be calculated based on the simulation study. In this module we'll see how power analysis can be done through simulation method. So first we'll see what is the rationale for simulation method to estimate statistical power. Estimating the sample size and statistical power of a study is an integral part of study design and has profound consequence for cost and statistical precision of a study. For standard design, power equations provide an efficient solution to the problem, but they are unavailable for many complex study designs and that arise in practice. So, for example, the multiple treatment interventions where one treatment is deployed at the group level and the second at the individual level, for such complex study design, computer simulation is a useful alternative for estimating study power. The main message from here is actually for calculating the power or calculating the sample size, you need a formula that is appropriate for that particular study design, and the formula varies over the different statistical tests that required for the study design. So sometimes for a very complicated study design you may not have a available formula to calculate the sample size or calculate the power. So that's why in those cases, those very complicated multi-level studies where available functions are not, or available formula is not there is no available formula or functions to calculate sample size or power calculation, the simulation method is a beautiful alternative for that. The method is universally applicable to a broad range of outcomes and designs, and it easily accommodates complex design features such as different follow-up plans, multiple treatment interventions, different site-specific cluster effects, and simulation can be or can also estimate the expected impact of deviation from optimal study implementation, such as time non-response and particular dropout, etc. If I give one example that might give you a clear idea. Suppose we are going to conducting a multi-level study where the sample was generated by a multi-level sampling methods, like you selected, say in India, you selected 3 states from India. From 3 states you select 3 districts from each state, and you select few blocks from say 3 blocks from each district, and 3 villages from each blocks, and say 10 households from each blocks, and all members of the households included in the study. Such a multi-level studies might require a multi-level modeling, a mixed effect modeling, and the power calculation may not be easy for this particular design. And so the simulation might be a very good alternative for this type of complicated study design. Here is another example I am using for Arnold et al. BMC Medical Research Methodology 2011, 11 to 94 pages. This is the reference. From there I took this and borrowed this example. They considered a study designed to test the independent and combined effects of environmental intervention, sanitation, hand washing and water treatment, and nutrient supplementation on child growth measured by length or height. The nutritionists have hypothesized that the nutrient supplementation interventions could be enhanced by complementary household environmental interventions that reduce the fecal bacteria ingestions during the first years of life and potentially improve gut health. To test this hypothesis, they considered a two treatment factorial trial in rural Bangladesh, where children less than 6 months of age are randomly assigned to one of 4 groups. The control, no treatment actually, the sanitation mobilization, lipid based nutrient supplementation and sanitation plus lipid based nutrient supplementation LNS. This design makes power calculation difficult for 2 reasons. One is, first, the treatment are deployed at different levels, community and household levels, and second, there are 2 sources of correlation in outcome, within community and within child. For illustration, let's consider a community randomized intervention trial to evaluate the impact of sanitation mobilization campaign on child height, where child height is measured once post intervention. Let Yij be the standardized height for age Z score for child J living in community I, and treatment AI is randomly assigned at the community level with equal probability. So let's assume the model as Yij equals to mu plus beta 1 AI plus Bi plus epsilon ij, where mu is the mean height for age in the control children, beta 1 is the estimated difference in height for age Z score comparing intervention children A equals to 1 to the control children A equals to 0. Bi is the cluster level random effect, and epsilon I is an error term that captures the individual level variability, the inter-individual variability and measurement error. Now assume that the random effect and error terms are normally distributed with mean 0 and known standard deviation and are uncorrelated. That is, Bi follow normal 0 sigma g, epsilon ij follow normal 0 sigma e, and covariance of Bi and epsilon ij equals to 0. The parameter of interest are mu, mu g and sigma e. To simulate the data, we need the estimates of those parameters either from the test dataset or from previously available datasets. So either you have to go through the literatures to get the guess of these estimates, or you can do a pilot study, and this pilot study might give you the estimate of this. That may not be a significant estimate, but you will get an idea about the estimates of these parameters, and that estimates can be used to simulate the data. So estimate the parameter mu, sigma g, sigma e from a training dataset or collected from previous literature, then create a population of 2000 children, 2 arms into 100 clusters or arm, and into 10 children per cluster. Within a unique ID variable for each cluster, a unique ID variable for each child, and an indicator for assigned treatment, say treatment A equals to 1 and A equals to 0. Generate a random effect for each cluster, the 200 total, Bi, which is a draw from a normal distribution with mean 0 and standard deviation of sigma g. Now generate a residual error term for each child Eij, which is a draw from a normal distribution with mean 0 and standard deviation sigma e. Then simulate an outcome for each child Yij using the model described before. The regress Yij on the treatment indicator Ai using the robust sandwich standard error to calculate for clustering at the highest level of correlation and store the one or two sided p-value for the test beta 1 equals to 0. Repeat the step 3 through 6 a large number of times, say at least 1000 times. Then the empirical power of design is the fraction of p-values that are smaller than 0.05. So actually you can develop a function that will return the fraction of p-values less than 0.05 out of 1000, and that would be your power. Let's do a case study. Now we will develop a function f in power in R passing the following arguments: the mu, beta, the SD cluster, the SD residual, n child per cluster, n treatment per cluster, n control per cluster, in iterations, the number of iterations for simulation. So develop a function that will generate the data as per simulation scheme described at calling from inside of the f in power function. Feed the ordinary least square of outcome on treatment variable using function OLS from RMS package. Using the Haber-White method to adjust the variance covariance matrix of a feed from maximum likelihood or least squares to correct for heteroscedasticity and for correlated response from cluster samples. The method uses the ordinary estimates of regression coefficients and other parameters of the model, but involves correcting the covariance matrix for model specifically and sampling design. The model misspecification and sampling matrix for model misspecification and sampling design. One can use Robcov function to generate to estimate the corrected variance covariance matrix. It accepts OLS object. So here is the function I am defining. As first I am generating a simulating data, just specify the value of mu, beta, SD cluster, SD residual, SD child per in child per cluster, in treatment per cluster, in control cluster per cluster, and then in cluster is equals to in treatment cluster plus in control cluster. Then in observation is equals to n child per cluster into n cluster, and double x is defined as matrix not available. Number of observations and columns are 3. So xx1 is the replicate 1 to n cluster, each n child per cluster, and x2 the second column is 1 to n row of xx, and x3 is the c replicate 1 in the times is n treatment cluster into n child cluster times, and then comma replicate in 0 replicate 0 for n treatment cluster into n child per cluster. So 1 for the treatment and 0 for control that we have defined, and column names you can give cluster, child, and tx. So now cluster random effects can be generated from normal distribution by following code, and the residual also can be generated, the epsilon ij also can be generated from normal distribution with mean 0 and variance sigma residual, and then y equals to mu plus beta into triple x comma 3 plus cluster effect plus residual part that generated from normal distributions, and then return a data frame of y and xx, the design matrix as well as the outcome. that will simulate the data. Now fn power function, that again the same pass by values we are using here, that are already listed, and then using the number of iterations as n iteration, I equals to 1 to n iterations, then data generated from the simulation function, that every loop will generate a fresh data, and then we'll feed the OLS function here, ordinary least square function here, and then calculate the corrected variance covariance matrix from row functions. Then we'll get the p vector by this formula, and then beta vector for this formula, standard error vector for this formula. The power is actually then the length of p vector, where p vector is less than 0.05 divided by length of p vector. That means the number of p values less than 0.05 divided by total number of iteration. So then the returning value would be, say, power equals to p value, the power equals to power, then p equals to p vector, beta equals to beta vector, and standard error is standard error of vector. So this is one list it will generate. Now we can call this function, that is, you have to load the HMISE package and library RMS package, and now to calibrate the calibration of the function setting beta equals to 0, we will set the beta equals to 0 for this function, and I will see how much power is there. This power is coming around 0.05. so it can be calibrated now. It is stable function. And further you also can do take a histogram and the QQ plot of the p value. Then you can see whether the left panel actually includes the histogram of p values, and the right panel is the quantile plot of the p values against the uniform random variables. And such diagnostic plot using p values generated in a scenario where the null hypothesis is true and are usually to validate a simulation program. So it is clearly indicating that it is actually valid function you can use. Now the power curve can be generated. You can calculate the power curve here. Say take the sequence from 20 to 200 by 10, and I just took interval 10 only, but you can take 1 or 2 to get very smooth curve, because that might take a long time depending on the speed of the machine. So I just try to avoid the longer execution of the function, so deliberately I choose longer interval. So by 10 so I use the interval 20 to 200 by 10 to 20, 30, 40, 50 like this, and then I use the for loop for I equals to 1 to length of cluster per arm, and use this function call the function and stored in out variable. Okay, and then this out variable here I assign the out variable for this cluster, and then I use the lapply function to get the power this, and then the st variable that x1 will give you, and then that this cluster per arm against cluster per arm, the unleashed power variables would be plotted, and then y lab is this, x lab is this, 0 to 1, and this is the actually power function. So it might take a long time depending on how much interval that you are taking, but the power looks like this. So this is the one example and one case study for calculating the power of a study by simulation methods. So I think I tried to give you the concept of power calculation by simulation methods, and through this case study, hope that will be really helpful for you to calculate the power for your model or your study design that you are going to do. So end of this module, we have learned the rationale for using simulation method to estimate power or sample size calculations, and the related different study and complicated study design that might be might require the sample size calculation through simulation study. And also we have learned how to implement, how to code the simulation methods, or how to implement the simulation methods in R through a real life examples, real life study design in these particular presentations. Hope this might be very helpful. I just took one particular type of study design, but you can take any kind of study design, any kind of complicated model where you can apply the simulation study to calculate the power of the test.